I have to say that there's nothing ever so fitting hosting this event in a place like this. George Westinghouse came to this site just over 100 years ago to build an advanced manufacturing for that time facility. And since then, thousands of Hamilton families have and people in Hamilton worked in this area. It's a site where a lot of innovations have taken place and have helped the regional economy. But now, a century later, the site remains at the core of Hamilton's innovation ecosystem and manufacturing, not solely in traditional sense, but also in continues to drive in an advanced manufacturing area, drives our economy locally, provincially, and nationally. And this transformation is not only the manufacturing processes, but also has spread through the other innovation sectors in Southern Ontario. Now, university research is central to the innovation agendas, both for our province and our country. World-class centers, as many you will visit today, contribute tremendously to this economy and deliver value to our industry partners and through the unique R&D projects that we have in this area. And because of that, the Ontario government announced a $50 million partnership for 3 universities, McMaster, Western, and Waterloo, to develop further the skills and serve the companies here in Ontario through various initiatives. And we're working very closely with our industry partners to deliver on that. And I should point out that the architects of this initiative, we have Deputy Minister Giles Gerson here today, along with his colleague, the Assistant Deputy Minister John Marshall. They've given us a tremendous confidence in our ability to deliver and contribute to our economy locally. And capitalizing on our critical mass of expertise, both in talent and infrastructure, positions Ontario in a very strong way. And to learn more about these manufacturing activities that we have, that is reshaping our economy, we have the pleasure of having with us Dr. Michael Zeh from the Machine Tools and Production Technology at the Technical University of Munich. Dr. Zeh is a global leader in Industry 4.0 and the new age industrial production. His work spans both academic and industrial sectors, making him an ideal expert to share his knowledge with us today. Please join me in welcoming Dr. Michael Zeh.
Good morning, ladies and gentlemen, and thank you, Mr. Vice President, for this very kind introduction. Thanks also to my colleague, Professor Stephen Feldhuis, for the kind invitation. It's a great honor and pleasure for me to give this presentation this morning, being titled Industry 4.0 or 4.0, made tangible things within Industry 4.0. As at least to my perception, with Industry 4.0, we have a new phrase in production technology that needs explanation, that needs also research. What does it mean and what can we do with it? How can we benefit from it? That's what I would like to talk about in this presentation. First of all, I'd like to show you 3 images of where I'm coming from. The laboratory at Munich University of Technology, or also called Technical University of Munich, TUM. We have several locations in downtown Munich. However, the one I'm coming from is located north of Munich, about 15 kilometers north of the city center. You see it here, the Garching campus. Which was established from a green field, I can say, in the 1950s, with the nucleus being this research reactor over here, this research reactor to do research on neutrons and how to use them. a small atomic reactor, and later on several other departments and faculty were relocated to this small city of Garching. The first ones being chemistry and physics, later on mechanical engineering that I belong to joined over here, mathematics and computer science and some other research institutes. Finally, we got an underground connection here, underground line. And mechanical engineering, within mechanical engineering, together with my colleague Gunther Reinhardt, I'm doing research on production technology. With Gunther Reinhardt, more being focused on factory planning, technology management, human factors, bionics and others. Myself more on technologies, cutting, joining, and additive, and both of us have some overlap here in the mid-level on machine tools and robots. Here you see a view of our laboratory, about 3,000 square meters of floor space, and just some things in here. We have 2 big laser cells where we can do research on joining and cutting using lasers with full laser safety. The highest or the most powerful laser source has 8 kilowatts, so that needs a very thorough design of laser safety. We have also a dry room, a clean room and a dry room over here to do research on battery manufacturing, lithium-ion batteries that are used for electromobility, but also for what we call the energy transition towards green energy. The presentation is outlined as follows. I would like to give you my personal definition of Industry 4.0, or what I consider a very short definition. After that, I'll explain some approaches out of our machine tool research and show you how this is connected to Industry 4.0. I'll talk briefly about additive manufacturing being part of it, as I consider it. Artificial intelligence is a promising thing to take advantage of in production. And then I'll show you some examples of research and other companies and give recommendations how to tackle it. A definition in the nutshell, ladies and gentlemen, Industry 4.0. In Germany, we are convinced we invented the word. We created the word. That is because it was announced during an event during the 2011 Hanover Trade Show. Someone from our federal ministry, someone from industry, and someone from research, highly or well-known people, they kind of, in a form of conspiracy, said there is something new coming along the road, let's call it Industry 4.0, because it will shape a new era in production technology. We already have 3 of them, so there is a new one coming. And this is characterized by the following. It's characterized by connecting systems in production, by taking advantage of the data which is created when those systems communicate to each other. But the word, however, stands for an initiative, or first stood for an initiative of the federal German government in cooperation with industry, of course with the aim striving to secure Germany's top position by empowering it with respect to digital tools and methods. A goal is, among others, the so-called smart factory with some features that I will mention in detail later on. Again, here you see introduced in 2011, so it's already 6 years old, indicating some kind of a revolution. Did the revolution come? Did the situation change from one day to another? From one day to the next? I wouldn't say so. We are more in a phase of transition to a new era, and this transition could last a decade, 2 decades, or even longer than that. And we have time to prepare and get adjusted. To bring it to the point, networked systems of all kinds within and between factories as well as towards customers. These items and objects, we have been used already to call them cyber-physical systems or cyber-physical production systems. This word is a little bit older, meaning systems with some kind of computational power inside of them, some kind of intelligence, and above all, able to communicate. This creates data, this interconnected mode. So we are talking about big data approaches taking advantage of certain patterns in that data. And it will also allow for new business models. So companies have to be aware of remaining up to date, not losing their competitive position because someone else develops a new business model. For example, if someone would position himself between automobile manufacturers and customers in such a way that the customers just pick a vehicle on demand just when they need it. So that's my definition, and I could finish my presentation at this point because there is not more to say about what Industry 4.0 is. It's as simple and easy as that. However, the question is, what is it good for? Is it a new bubble that will explode soon, or can we take advantage of it? And certainly we can. Certainly we can. It's meant, or people think it's good for increase of flexibility, smarter integration of the workforce. We say meaningful work, meaning to take advantage of the intelligence and capabilities for fine manipulation of humans, but smarter integrate them, relieving them of high workloads just by carrying objects and things like that. More efficient use of resources, reduce time to market, improve competitiveness, and so forth. And if you look at this, it's nothing but CIM, computer integrated manufacturing reloaded, which we were talking about in the late 80s and early 90s. A computer does everything from the designer's idea until delivery and servicing of the product. This CIM approach failed. So basically, we start from scratch, or we start again. The good news is we have better methods, more developed methods, and better tools today than we used to have in the late 80s and 90s. So those who master it will have a competitive advantage. By the way, here are two new words that go along with it: Internet of Services, Internet of Things, as things communicate to each other. Or you could also say Internet of Everything. For decades, we have already been working on an important part of it, which is the digital shadow, as we call it. So it's a virtual representation of the objects that we are using in manufacturing. That means, for example, process models. That means finite element models to calculate a machine's vibrational behavior, discrete event simulation on the planning level, or disturbance management on the factory network level. We have been working and we have made progress in the design of these systems, and they now help us, again, to take advantage of Industry 4.0. I should say, took a look at what others say about it. Here is McKinsey's view, a consulting firm, saying that it's a next phase in digitization of the manufacturing sector, characterized by 4 disruptions: rise in data volumes, analytics and business intelligence capabilities, artificial intelligence, improved, more intelligent, smarter machine-human interaction, and digital instructions which are delivered to the physical world. Whenever you see publications in magazines about Industry 4.0, mostly there's one of those photographs, and I'm sure you have them in mind, where we see someone with a mobile device, a handheld device in front of a workshop or whatever. So that's one important feature, delivering instructions via digital media to people part of the workforce. So these 4 trends are not the reason for 4.0. The reason is this one here. We used to see a first industrial revolution based on steam power replacing human power and animal power in production. Later on, we had the era of mass production, mainly driven or heavily driven by 2 gentlemen, Taylor and Ford, with the approach of mechanized production and mass production. Since the late 60s and early 70s, the use of electronics and information technology for increased automation, however, still inflexible automation or widely inflexible automation. And now this 4th phase means flexible automation, Internet of Things, also in development. Innovations in machine tools. I'm basically a machine tool guy. I received my PhD on vibrational analysis of circular sewing machines, and also have an industrial background in the machine tool business. So this is kind of my favorite topic to talk about, and I'll show you some examples out of our research. How will machine tools benefit from that? What are the next steps to be done to make machine tools smarter, more productive? Vibrational behavior, self-excited vibrations, also known as chatter, will keep us busy as long as machine tools exist. That's what I'm convinced of, because everyone will always try to apply those machines at the highest productivity possible. So reach the stability border. What can we do to prevent these chatter vibrations from occurring? Here you see spindle housing of a machine tool vibrating in this direction. And one possible approach is to introduce active damping into this machine, meaning a shaker which is attached to this spindle head. On the right-hand side, here you see it, an acceleration sensor that detects the vibrations, and then we put this or make this part of a control loop and let this actuator introduce a force to the machine counteracting these vibrations. So once we switch this active vibrational control on, the displacements, the dynamic displacements go down. And you can see this here in this Fourier diagram, where we had a chatter vibration in the machine, controller being not active, and once switching on the controller was able to stabilize this self-excited vibration until it was no longer visible. What you see here as a peak is just the tooth pass frequency, which is not critical in this case. So with this simple approach, we can handle the problem. However, it requires a digital shadow of the machine. We need to know its vibrational behavior from a modal analysis or a finite element analysis. Machine tools can also be more efficiently used, more flexibly, in a more versatile mode, be used by introducing this process or this technology, friction stir welding. Probably some of you have already heard of it. It's a joining technology, a welding technology, which can be carried out in the solid state phase of a material. It works such that we have a tool consisting of a pin and a shoulder rotating. The pin will be pressed towards the two joining partners. You see the weld seam here in a butt joint configuration. And this introduces heat into the material, softening it, and that will allow to move the pin fully into the two workpieces, stir the softened material, and then traverse along the weld seam, which is then created here. Finally, you retract the tool. This nasty end crater remains. However, there are strategies to fill it up with other technologies. And then you have a beautiful weld seam with a high quality, no shielding gas is necessary. Dissimilar joints are possible between aluminum and steel, for example, between copper and aluminum, and even between plastics and metals. High process forces occur, these we have to handle, and it's not just as easy to move along an NC trajectory or NC path. We have to take additional measures. And one such measure is a temperature-controlled mode. Here you see in the lower half of the diagram, you see the situation that occurs when you do a conventional welding, just positioning the tool according to the geometry. This would end up with a high flash creation here. And the solution to that is to put a temperature sensor into the tool and use this again in a control loop, in a feedback loop, and carry the process out in a temperature-controlled mode. On the right-hand side, you see the improved situation with respect to flash creation. This is due to the fact that heat accumulation is avoided in this situation. Here in a workpiece with edges in some places, when you get closer to the edges, the air around it is kind of an insulation. And that creates heat accumulation, and that is being avoided with this setup here. This then yields a high tensile strength of the weld by the controller adjusting the process parameters automatically. Again, a digital shadow is needed here because we need to know the behavior of the material with respect to this process. And we also need a model of the machine controller so that this loop does not become unstable. The robot is becoming a machine tool more and more. The robot has several advantages and also, not to be forgotten, disadvantages over conventional machine tools. Advantages are the high working area in relation to the floor space being consumed, excellent space utilization, low investment costs compared to a machine tool. Imagine this work area that this robot, KUKA 2500, can cover compared to a machine tool. The machine tool's costs would be much higher than these 80,000 euro or $100,000, what this would convert to. However, the repeatability is not good enough, and even when cutting aluminum, we have a static deviation in the range of a millimeter, and this is certainly not acceptable. So we need strategies to overcome this. And concerning the static deformations, we can say, okay, let's take the axis signals, use them as sensors for displacements of the robot, and then process the signal to compensate for this deformation, and have a signal which is to be superimposed, a correction value, to be superimposed to the tool path. This has this is working. We demonstrated that this is working. However, it has difficulties upon entry and exit of the tool into the workpiece when the situation changes rapidly. So another idea is to simulate the behavior of the robot based on a model, digital shadow, and modify the robot control code prior to machining. And that's what we are currently working on. We were also working on the issue of chatter vibrations here. And from literature, we have 3 strategies to avoid those chatter besides active damping, which I showed you before. Conventional approaches you see here. Make use of the stability lobes or pockets. Very promising, very easy to apply. Periodic spindle speed variation, good on machine tools, unfortunately not good for robots because this introduces additional vibrations into the robot. Unevenly spaced cutters, promising, it does work. However, when optimizing the teeth spacing, the angles between the teeth, you end up with very awkward spacing, such as the 13 degrees or 17 degrees in a 4-teeth cutter. So in many cases, it's not possible to select the optimum teeth spacing. Again, Digital Shadow helps to design such a tool. And finally, the Digital Shadow for the thermal behavior of a machine tool. Now, it's already enough of an effort to design a finite element model for a machine tool to calculate the vibrational behavior or static deformations. Would anyone want to take the additional effort to create a new model for the thermal behavior? Probably not. So the idea is, and one of my PhD students came up with this, to use the mechanical finite element model and convert this into a thermal model. What's necessary to do that? It's necessary to identify surfaces of the components and to introduce the thermal transport phenomena, such as convection, conduction, in the components and between them. And you have the model. And this demonstrated to be valid and capable of simulating the thermal behavior of the machine tool, the thermal digital shadow. Additive manufacturing is part of it, everything being connected. That has always been the case for additive manufacturing, because we need a 3D CAD model of the workpiece to be manufactured. Only works from 3D CAD. So you can apply additive manufacturing, or 3D printing as it's sometimes called. Also in this connected mode, design a part here, send the model to Singapore and print the part there. It's a matter of minutes to transfer the data to different places, to all other places in the world. You're familiar with the process sequence used in powder bed additive manufacturing. Once you have your 3D CAD model, you triangulize this and you slice it into virtual slices. If necessary, create the supports in the model and then transfer the result to the machine, which manufactures the workpiece slice by slice, layer by layer. In the end, cleaning is necessary, removal of the power not being solidified, and finishing process. So it's a completely integrated process chain which perfectly fits into Industry 4.0. And it opens completely new possibilities, in particular because geometric features are coming for free. What you pay for, the costs, stem from the part volume, not from the design, shape, and number of its features. And you also have the possibility to manufacture parts that are connected to each other and movable towards each other. So what you see here is coming out of a research project together with my colleagues Fraunhofer Institute. A research project demonstrating how this can be benefited from in the design and manufacture of gears. First of all, you see the lightweight design with this topology optimized structure, and you see conformal cooling channels delivering the coolant just below the surface and delivering it at the teeth contact where it's mostly needed, primarily needed. Here you see the parameters of the process. The result was that we have a 25% mass reduction, conformal cooling for high temperature transmission, and shorter lead times in production. Second example is coming from a tool manufacturer. You see here a reaming tool, reamer tool, or reamer, in the conventional design. And the issue here for the company was that this is susceptible to chatter vibrations, or let's say high amplitude vibrations, because it has quite a high mass. And the idea was to reduce the mass with this lightweight design, which would certainly not be feasible for conventional manufacturing technologies. Imagine you would have to drill these holes here and so forth. So additive and this perfectly go hand in hand with each other. Here you see again the parameters, standard steel alloy SLM machine, and the process was shortly after completion of the project adopted by the manufacturer, the MAPA company, achieving a 54% mass reduction, lower vibration amplitudes when applying this tool. This is coming out of research, still in the research phase. We are able to do what we call bionics, learning from biological structures. How do they accomplish lightweight design? For example, using honeycombs, and we came up with a procedure, a data manipulation procedure to fill a support structure with honeycombs, as you can see here, and this structure can be arbitrarily designed, more or less. This also required a digital shadow here in order to simulate heat accumulation, heat-induced distortions in these honeycomb structures. This indicates or demonstrates that we have a model at hand to calculate those distortions and avoid them in a trial and error procedure. I also included this picture in my presentation, though it's not coming out of our lab, because I wanted to show you another additive procedure and additive manufacturing process which is not powder bed based and which has the great advantage that any kind of distortions coming from heat, which is needed to melt the powder, any such distortion can be removed immediately because we have an alternating adding, 3D printing, and removing by a milling process, for example. DMG Mori introduced this a couple of years ago, also during the Hanover trade show. I think it was during the EMO, another machine tool show. And this is a very, very interesting process which allows to manufacture filigree structures such as this one very rapidly and very accurately. Artificial intelligence is a promising thing. And what is artificial intelligence, ladies and gentlemen? It is again learning from biology or humans. How do we learn to walk as children? By trial and error, and by connecting neurons in our brain in a certain way, and then just replicating this. So artificial neural networks. And nature does learn by evolution. We as humans have developed from evolution by the principle survival of the fittest, and we can apply the same principle in production. I want to demonstrate that using two examples, one coming from planning tasks and another one coming from more or less the shop floor. The one from planning is taken from an industrial project that we were working together in about 14 years ago. A manufacturer of household appliances with his factory for dishwashers west of Munich. And the logistics situation is such that demand from the market is being collected by dealers, by distribution centers, then communicated to the factory, to production, and then the demand from all those distribution centers and so forth are collected to certain production orders, and then after manufacturing, of course, shipped to those centers. Planning for a day's load of work was manual before the project. That means there was a person in charge of the task to dispatch all the orders for a day to 8 different lines of assembly. The manufacturer has 8 different lines of assembly with different capacities and different capabilities. And of course, changeover and capacity load for those lines was the issue. Changeover times between two orders, because every time you change over from one order to the other, all the unnecessary components have to be moved back to the warehouse, and the new components have to be brought from the warehouse. So this is cost and effort. And it took this person about 2 hours every day to carry out this planning task. An SAP dialog did support that, but still required the creativity of the person in charge and 2 hours of his time. And the idea was to set up an evolutionary algorithm to suggest solutions for the problem. An evolutionary algorithm, what's that? It's basically a program loop which starts with a randomly set initial population, which would be a certain way these orders are dispatched to the lines, completely randomized or arbitrarily. Then a fitness function is calculated that you see here, and basically it sums up all the changeover efforts from one order to another for all orders, for all lines. And an additional function can be used to penalize, for example, line overload or lateness of an order and things like that. And then it selects a portion of the best of the individuals, taking the best of them, selection, as parents for the next generation. Then again, random comes into play. That means applying random changes to these solutions and create the next generation, the offspring. Check this towards an abort criterion. Is the fitness function below a certain threshold? If yes, stop and take this as your solution. If no, continue the iteration. So it's mutation, it's selection and recombination, and it's mutation and reproduction. How we, as humans, evolved from nature. And when implementing this, it became obvious that abort criterion is reached within a very low number of iterations, 10 in this case, and now no matter how bad the initial solution was, the algorithm would always end up with a very, very good solution, reducing the workload for the person to 10 minutes per day, and it's in use at this manufacturer since the year 2005. Ended up in reduced costs for material and line use, allowing for more meaningful work of this person. Second example, a structure that can be welded. It's an arbitrary structure representing all kinds of frameworks that need to be welded, are made from sheet metal, for example, and need to be welded. In this case, using lasers for creating the weld seams. And here you see 4 such pieces of sheet metal. And in work before, we established finite element models to calculate the distortions coming from the heat. And that's the issue here. Because you would want to close your framework, such kinds of frameworks, in the end without any tension or without any strains or stresses, without any distortion between the two ends. Normally, you end up with a distortion, and you would want to minimize that. We established heat source models required for the finite element calculation and the finite element models for the weld seams. However, the task to minimize these distortions is not trivial, because you have many process parameters, and many different sequences of welding. And here the approach of my PhD candidate with the thesis to be published within a few months from now, the approach was to have an artificial neural network which learns from a few finite element calculations, because calculating all possible combinations of parameters, sequences, and so forth would take months, if not more than that. So that's not feasible. So the idea is to just take a few such simulations to train an artificial neural network. Neurons need to be connected, with each of them having a certain mathematical function behind. So the neural network learns to replace the finite element calculation. However, it in itself is not capable to optimize. For that, he is using an evolutionary algorithm which selects, recombines, mutates the parameters which are then fed to the artificial neural network in order to come up with the solution for the distortions, and then this whole thing optimizes. You see the results on the right-hand side. Upper picture shows just a random parameter setting with the distortions. Don't be confused by this big gap here. This big gap was left intentionally to make the whole thing better visible in such a picture. The distortion is the vertical one here between the two ends. And the process is optimizing this, achieving a situation such that the two ends have the same height in vertical direction. That's artificial intelligence. Now, coming to the next point, what has already been done? How are enterprises taking advantage of that? Two examples from industry, two from academia, or cooperation between academia and industry. Bosch Group, Rexroth Bosch Group, a manufacturer of hydraulic equipment, fittings, valves, and things like that. This was published a while ago as a case study. Bosch Rexroth is implementing Industry 4.0 on the shop floor step by step, small but quick steps. Important. You can't attack everything at a time. You have to select what is promising for your enterprise and then try to take advantage of that as quickly as possible. Gain experience in pilot projects. Within the group, there are 100 or more such projects. In this case, you see here a semi-automatic production line with more than 200 different valves to be manufactured. Flexibility is needed. Automation, yes, but in a flexible mode. The workpieces do identify themselves by an RFID tag, and this enterprise, among many others, contributes to something which is very important, the establishment of standards for the communication interfaces. General Electric company is doing the same thing, also contributing to standards. They say that Industry 4.0, there is definitely significance in it for the enterprise, in particular in the Internet of Things, and they are trying to apply this to carry out their customer service in a better way. In the past, or up to now, they used to use a repair-oriented approach. When something breaks down, it needs repair, and they want to make the transition to more of a predict and prevent model with respect to that. Meaningful work, meaning relieving the workforce of high loads to be carried. This was explored in a project funded by the European Union that we were in this project we were partly working in together with these other enterprises that you see here. Loewe is quite well-known manufacturer of television screens, and there are many environments where you have heavy loads to carry and put into a box. Just the packing task is something which does not really take advantage of the capabilities of humans. And the idea is here to carry the high load using a robot, and the humans will do the fine maneuvering and fine manipulation, and also take care that the right stuff is being packed into the box, because we have different models that require different operation manuals and so forth, different remote control. Here you see sink and household equipment. Currently, we are working together with machine tool builders and tool builders to establish an interface for tools and machine tools, tools and spindles. Here you see a number of German tool manufacturers and component manufacturers for machine tools, and the idea is to have an interface that is capable to transport the data coming from sensors in a tool to the machine. Internet of Things. Tool communicates with the machine. And feedback signals such as, for example, for ultrasound-assisted manufacturing, ultrasonic cutting, which reduces the cutting forces. And of course, there's many other things that you could transmit through this interface. We call it, or I call it, the USB interface for tools, like your USB device. You just plug it and play, or plug and produce. How to tackle it? What would be the recommendations? 4 slides here. First one, taking a look at big data, additional value. Is that possible? And as an enterprise, I would ask the question, is data already acquired and stored, for example, because of legal regulations or because of customer requirements, because of traceability issues in pharmaceutics or aircraft manufacturing or whatever? Other legal regulations, are tool monitoring systems in use? If so, the question is which conclusions can be drawn from that, which analysis is desirable, is data missing, and if so, which kind of, and how can it be gathered? Look for quick wins in the field of big data, just do it. And a fruitful environment would certainly be a brainstorming session, a workshop, if possible, with academia. On the shop floor, is data from tool monitoring systems available? Can one benefit from modern tools or processes, also such as additive manufacturing, the reaming tool in the set of my examples? Joint application of machine tools and robots, for example, the robot servicing the machine, removing chips, exchanging a workpiece or a tool, question mark. And can you apply robots to support your workforce, for example, so that the workforce is able to do more meaningful work? Are there potentials in sales, supply chain management, customer service, the so-called indirect parts of the factory? Is monitoring of your supply chain possible via network? Kanban, just-in-time delivery possible? Data entry by the customer? The company I used to work for, the Gleason Works, with their headquarters in Rochester, New York, I was employee of a German subsidiary, had a solution for that already in the 90s, when dealers could enter orders for tools via the internet, and these tools would be produced in the factory with no further interaction of humans. Data entry by the customer, more or less, or at least, let's say, by the dealer, the sales agency. Are there new business models, new opportunities to take advantage of? And for machine tool builders, machine tools are today mostly controlled using personal computers. That in itself is Industry 4.0 compatible, so it can transfer data to the machine tool supplier and allow for evaluation of this data. Other unused potentials, are there unused potentials, for example, concerning paperwork, repeated generation of the same geometrical data of workpieces, or are there possibilities of artificial intelligence and so forth? I hope I could convince you that Industry 4.0 is something very simple to explain. Objectives are, among others, increased flexibility in production down to lot size 1 manufacturing scenarios, increased productivity, reduced time to market. I'm convinced, by the way, it's not a job killer, it's a job creator for those who learn how to handle it smartly, who use it wisely, not all at a time, but piece by piece, step by step. It's not a revolution that changes the world from today to tomorrow. Everyone still has a chance to come aboard. However, everything has to be developed and earned. There is very little that you can buy off the shelf. Sensors, actuators, that kind of stuff, even additive manufacturing machines, those are available. But to tailor it to your enterprise, you have to do that by yourself. Germany, where I'm coming from, has, I would say, done quite well up to now. We came through the 2008-2009 financial crisis quite well because we have 25% of our GDP coming from manufacturing, which is quite high, much higher than, for example, Italy, France, UK, our direct neighbors. And we have a very good funding scheme, very good support from politics, from government, funding both academic research and industry cooperation in a smart balance, I would say. Taking a particular look at the machine tool, does that mean that today's machine tools are obsolete? Will they look completely different in the future, those machine tools? I wouldn't say so. They will look pretty much the same as today, like this one here, or like the robot being a machine tool. They will just have the better inner values. And that concludes my presentation, ladies and gentlemen. Thank you very much.